Yeah, hello everybody. This is part two of the video which I posted a couple of weeks ago regarding the theory of the aerodynamic lift. So, in the previous discussion, we learned the mechanism of the aerodynamic lift, which is dominantly the low pressure generated on the upper surface of the wing. This is Bernoulli mechanism, and about also the Newtonian contribution into the aerodynamic lift. So what we are going to do today is first of all review what we have discussed last time, and we will present today the Lancaster-Prandtl theory of the aerodynamic lift, which I promised in my previous presentation. So let us come to this topic. So this is this is the title, the mechanism of the aerodynamic lift. So what we are going to do is to first review the previous the presentation, and then I will discuss a misconception in the literature about the application of the Bernoulli's theorem, which is very important. And then we will discuss the correct theory of the aerodynamic lift, which is called the Lancaster-Prandtl theory, which is also called the circulation theory of the lift. And then we will also discuss the Kota-Jakowski condition, okay, which is the must condition for a smooth flow over the airfoil. And then we'll also discuss a little bit about the stall, aerodynamic stall. So let us review first what we have learned last time. So we said that the aerodynamic lift can be understood in two ways. One is the Newtonian way, and then another one is the Bernoulli's way. So in Newtonian way, one argues that the airfoil actually deflects this air in the downward direction. So if this is the wing from a side view, and suppose that the aeroplane is moving in this direction with some velocity v, and what happens is that the air is bent. Actually, the airstream is bent downward by this because of the angle of attack. So this streamlines are bent in the downward direction. That is the direction of the flow of the air, which is horizontal here with respect to the wing, and it is now, when it flows over the wing, it is now deflected a little bit in the downward direction. So there is action by the wing on the airstream. So then by the Newton's law, there must be reaction by the airstream on the wing. So that there must be a force, upward force. Okay, but this is not the dominating mechanism. It is definitely present, but it is not the dominating mechanism. The dominating mechanism is due to the low pressure generated on the upper surface of the wing. Yeah, because when it's a very peculiar shape of the profile. So what happens is that which I am going to explain today, that there is a faster flow over the top of the wing, and there is a slower flow in the lower of the wing. Because of the faster flow, there is a region in the upper surface of the wing. This region is of low pressure region, and here you have the high pressure, and then due to this pressure difference, there is aerodynamic lift. This is the dominating component, or you can say that this is 80%, okay, and this is only the 20%. So this is the dominating and the main governing mechanism. Now the question which was not addressed last time, actually I deliberately skipped the question, and because I wanted to first explain these two competing views, and this is what is the most relevant one here. So the question is, what is the reason that the air flow is faster over the top of the wing? This is a question which has been discussed in the literature quite a lot, and the problem is that most of the explanations are wrong in the literature. They are fundamentally flawed. So today I'm going to tell you the correct explanation, but before that, let us discuss an explanation which is generally given in textbooks, and but that is the explanation which is fundamentally flawed actually, and it has a problem. So I will tell you why it is problematic. So what is argued in the standard literature is that, so they argue that because of the curvature of the wing, the air parcels has to travel a longer distance. If you see, this distance is larger than this distance. So if this is A, this is B point, say this is point C, and this is point A dash, this is B dash, say this is point C dash. So the length actually A, B, C, this length total, this length is much bigger than the path. This is A dash, B dash is bigger than A dash, B dash, C dash. So they argue that the air parcels which actually depart, if you consider two air parcels, one here, another here, these air parcels, if they depart here, and then this air parcel has to travel longer distance as compared to the air parcel which follows the path A dash, B dash, C dash. Okay, and then it is argued that because this parcel has to travel a longer distance, hence it has to travel faster so that they reach here at the same time. Okay, it has to travel faster. This means that the air must flow very fast over the top of the wing, and as I discussed last time in the Bernoulli's theorem, the faster air means lower pressure means aerodynamic lift. Okay, but this is this explanation is wrong, because one thing which is known is that the two air parcels A and A dash, if they depart from the leading edge, they never meet at the trailing edge. The parcels which flow over the top, they reach much earlier as compared to this compared to the parcel which flows underneath the wing. So the parcel, for example, at t equal to 0, the parcels are here, the upper parcel will be here, the lower parcel will be here at some t equal to t1, and then say at t equal to t3, this parcel will be here and this parcel will be here, the air parcel will be here. So they never reach at the same time. Okay, so that is the truth actually. This has been seen in simulations and real experiments. So in the literature, which is based upon the argument that because the air parcel has to travel a longer distance on the upper surface, hence it has to speed up, it is wrong. Okay, you can easily see that the air parcels are not intelligent beings. They don't have any intelligence. So there is no reason that if they depart here, they have to meet here. They never meet actually. They never meet in the trailing edge. So the explanation given in the literature that the air parcels meet here at the end and the upper parcel has to travel a longer distance is wrong. Okay, now the question is, if this is clear, the second question is why. The question which is very important, the central one, is why the air is to move faster over the top of the wing. What is the reason? The reason lies in this Lancaster-Prandtl circulation theory, which we will discuss now. Okay, so I have up to now I have reviewed what we studied last time about the Newtonian way and the Bernoulli way. And then there is a misconception which we discussed and which we clarified. The misconception is that the air parcel has to travel faster on the top of the wing because it has to travel more distance. This is wrong. Air parcels are not intelligent beings. Okay. In fact, what happened is that the air parcel which is flowing over the top, they always reach earlier at the trailing edge than as compared to the parcel which flow down. Now the question is that why there is a speed up, why the air moves faster on the top of the wing. This is a question which we will address now through the Lancaster-Prandtl circulation theory of lift. So simply called the circulation theory, the circulation theory of lift. Circulation theory of lift. So what happens is the following. It is given in this way. So there are two ingredients which one has to very clearly appreciate. One is the starting condition. So there are two ingredients which we have to distinguish very clearly. Starting condition. Then there is a very important theorem due to Helmholtz. The Helmholtz theorem. These two points we have to take into account. So I will tell what is Helmholtz theorem, which is very simple. We'll explain it along the way. So let us focus here on a wing profile which is at a finite angle of attack. So this is a wing profile and it is at rest. Suppose that it is at rest. Now the point is that when it begins to start, the thing is that there is a vortex generated here in the trailing edge. So the reason of the vortex is, so let me first tell you what happens, and then I will explain why it happens. So the point is that there is a vortex generated here. Once the wing begins to start at a finite angle of attack, there is a vortex generated. If this vortex is in this way, which is counterclockwise, there is a anti-vortex generated. So we call it vortex here, and then you have the anti-vortex. Okay, now the question is, why there is a vortex generated when the plane starts, or when the flow starts over the wing profile. The reason is this. What happens is that you see that when the air streams are coming like this, they are getting squeezed here on the upper surface of the wing. There is a squeezing effect here over there, and then it is opening up in this way. At the same time, in the trailing edge, below the wing, actually, at the trailing edge, there is a squeezing effect. Because of this angle of attack, there is a squeezing effect, and due to this squeezing effect, there is a little slight higher velocity of the speed when it leaves below the wing. So there is a slightly higher velocity below the wing surface as compared to the wind velocity at the upper surface. So there is a slip, actually. There is a slip. The reason is because you have higher speed here and your lower speed here, then there is a tendency to curl up. So there is a tendency that you make a vortex here, because the faster air tries to fill up like this, and this is actually the reason behind this vortex generation is viscosity. Every layer in the airstream, if you look, every layer in the airstream, it talks to each other because of the viscosity. There is a viscosity which is kind of friction between the layers of the air. So due to this viscosity, there is a curl up tendency, and you get a vortex here. Actual simulations I have in the end of this video. I will show a link where actual simulation has been done, where you can see a real experiment has been done, where you can really see the formation of the vortex. There is a video, actually very old video, by Prandtl himself, who is the pioneer of this theory, which is the mainstream theory. And because of this vortex, and then there must be anti-vortex. This is the Helmholtz theorem. So Helmholtz theorem says that if there is a vortex, there has to be anti-vortex. So the point is that net vorticity is conserved. It's a conservation principle. You can say that net vorticity must be conserved, okay, in an ideal fluid. Okay, roughly speaking, if you have a vortex which is moving like this, there must be anti-vortex which is over the wing, which is in the clockwise direction over the wing. Now you see, if the air is moving in this way and the vortex have this kind of orientation, you have the adding up tendency on the top of the wing, and then you have sort of cancelling tendency at the bottom of the wing, because due to vortex the air tends to go this way, but then there is a airstream coming in this way. There is a cancellation tendency at the lower surface, and then there is add up tendency at the upper surface. So what happens is that you get a very high speed on the top of the wing, and you get low speed at the bottom. This velocity is much greater than this the velocity due to vorticity. If this is V1 and this is V2, the V1 is greater than V2. Okay, so there is a net airflow in this direction only, but this airflow is much slower as compared to the air which flows on the top of the wing. This is the crux of the matter, and this is called the Lancaster-Prandtl theory. Now what happens is that when you start the wing, so there is a vortex generation. This initial vortex will depart. It will be left behind once you have a steady state condition reached. So the thing is that the air streams, you have this initial vortex, and then you have this airstream going like this over the top like this, and these are the under the wing. So the point is that you have here, what happens is that initially because here there is a squeezing effect just below the tail of the wing, and later on because this vortex is generated, later on there is a higher speed on the top of the wing because of this addition of these two, they at one point after this initial transient, what happens is that you have a smooth condition at the trailing edge. By smooth condition we mean that the velocity with which the air flows below the wing must be equal to the flow at the above the wing, at the trailing edge. We are talking about at the trailing edge. So once you have this smooth endpoint, this condition is called Kuta-Jakovsky condition. These are the two mathematicians who pointed out this condition. This is one of them is German mathematician Kuta, and then this is a Russian mathematician who pointed out this peculiar condition at the trailing edge. So in this region you have very high speed of the air, in this region lower speed, but the trailing edge the speeds becomes equal and you don't have any vortex here anymore, and the flow is smoothly leaving the trailing edge. So due to this low pressure here, because high speed, low pressure here, you have a aerodynamic lift by the Bernoulli's theorem. So this is the lift force. So that is what is behind the aerodynamic lift. It is definitely Bernoulli's theorem, and the speed of the air above the wing is not due to distance argument, which has been pointed out in textbooks or in many discussions, that the air has to move faster on the top of the wing because it has to travel more distance. This is wrong. The real reason is that when the wing begins to start, it generates a vortex, and at the same time, by the Helmholtz theorem, it also generates an anti-vortex. So due to anti-vortex, the speeds adds up on the upper surface, and due to this adding up of the speed, you have a higher speed at the upper surface, but there is a cancellation of the speeds below the wing, and you have lower speed at the bottom of the wing. Because of the lower speed here and higher speed here, you have lower pressure here and higher pressure here, lower pressure here, you have the aerodynamic lift. This is the dominating component, as we discussed before. Newtonian component is much less, and this is the major component, or they also call suction lift, because this is sort of taken up due to the low pressure wake here, and that is the real mechanism of the aerodynamic lift. Okay, so let me discuss one more topic of the aerodynamic stall in this very introductory, very brief sort of presentation. So if we consider a small angle of attack, if you have a small angle of attack, so in a smooth conditions, so the flow is smooth, nice smooth over the upper surface, it leaves the trailing edge smoothly, and similarly the flow is smooth on the below the wing. Okay, and this is called the angle of attack. So this is called the chord. The line which joins the leading edge and trailing edge is called chord, and this is the horizon or horizontal line, and this angle is theta, is called the angle of attack. Okay, now if you plot the lift, if you plot on the x-axis theta, the angle of attack, and on the vertical axis you plot the aerodynamic lift FL, let's say the aerodynamic lift FL. So what happens is that if you have a cambered airfoil, even at zero angle of attack, there is a lift. Actually there is a lift, so the lift increases when you increase the angle of attack. So but this trend is not continuous. At a particular angle, which is called, say, theta s, which is called the stall angle, the lift becomes to suddenly reduce, and so you have loss of the aerodynamic lift, and which is dangerous for a stable motion of the aeroplane. So one can increase theta up to a certain level, but it cannot be increased beyond this cutoff angle, which is called theta s, the stall angle. So what happens is that, as you must be knowing, at a large angle of attack, the flow is okay below the wing, it is okay smooth, but what happens is that due to the viscosity of the air, the flow starts to separate. So here you begins to get eddies. So these are the eddies which are generated due to the flow separation. So we call it flow separation, and due to this flow separation you get eddies, and these eddies destroy the low pressure over the upper surface, because these eddies, you know, in the eddy there is a airflow which is going in this direction. So this kills the speed on the upper surface of the wing, and then if there is no high speed on the upper surface, the low pressure region is killed. These eddies kill this low pressure region, and you don't have the aerodynamic lift anymore. And after that, theta s, you have a sudden drop of the aerodynamic lift. So this is called the stall angle. So and then also there is a topic of drag, and there is a relationship between drag and lift which is generally proportional at a lower angle of attack. And then there are other complications into the theory of the aerodynamic lift, which I will not go into technical details. There are various there are other subtle points which is called the downwash, stuff like that, tip over vortices, stuff like that, because the wings has a finite length, they don't have the infinite length. So all those technical details are skipped, but they are available in any aerodynamic book. Actually, you can study those topics. So my main purpose in this short video lectures was to present you the correct mechanism of the aerodynamic lift, and I wanted to clarify certain misconceptions. So let me close this video by one more time reviewing what I have discussed. So you can rationalize the aerodynamic lift into two ways. One is Newtonian, another is Bernoulli's way. In the Newtonian, it is a downward deflection of the wind, and due to this downward deflection, you have a action and then the reaction. But this action or reaction component is very minor. It is only 20 to 10, maybe 10%, maybe 20%, depending on the angle of attack and nature of the wing. The major component is the low pressure generated due to the high speed on the top of the wing. This is the main component of the aerodynamic lift. And the reason which people give is that why there is a high speed on the top of the wing is that they argue that because of the camber, or the very special shape of the upper surface, the air parcels has to travel a longer distance, and hence they must move faster. This is wrong, because they are not living beings. They have to move faster. This is incorrect. The correct way to understand is the vortex and anti-vortex generation. When the wing begins to start, it generates a vortex. In response to this vortex, there is anti-vortex generation. This is a conservation principle captured by the Helmholtz theorem. And once there is an anti-vortex on the surface of the wing, you can easily see that the air speed is in the